Welcome back to the series of lectures on high performance scientific computing. So far we have been discussing several tools with which we can improve our performance of our codes. These tools also helped us to analyze the code to see where the pain points of the code or the hotspots of the codes are, from where we can put in our efforts to sort of accelerate them or further optimize them. But sometimes we are in a scenario where your code is maybe optimal, maybe there's no further optimization that you're going to do, but for some reason is giving you some wrong results. And this is not due to some compilation errors. This is due to some sort of ideological bug that you have introduced in your code, some problem with the logic that you're using in your algorithm. And sometimes you have to sort of slowly step through the code to see how different variables are getting updated to check whether my code is doing what I really want it to do. This sort of debugging is very difficult, and for this we have a very useful debugger called GDB. GDB, or the GNU debugger, is a powerful command line debugger. It is very, very essential to see how a program particularly behaves. And this is really important in trying to fix logical bugs. Bugs which cannot be caught by the compiler, and bugs which we have to sort of work very hard to figure out. So essentially the reason why you want to use GDB is that you want to do a step-by-step execution of your code. You want to do variable inspection at different times of your program, where you have to go in between and check to see where my code is malfunctioning. I would like to do breakpoint setting, in the sense that I would say the code to sort of momentarily take a pause at a particular line and then go and check what the different variables are, how they have been computed, and if something is going wrong at that point of time. So this sort of memory analysis is to be done by GDB. Now GDB is available in pretty much all the operating systems, Linux, Mac OS and Windows. So it's essentially platform independent. This is a great tool for us to use to debug programs. We will now see how to use GDB. So first of all, to use GDB, you need to give the compiler information that you need to put in debugging symbols. Essentially, these are tools for GDB to pick up, and the compiler needs to know that it needs to introduce this into the executable. So for that, you would compile either your C or C++ code with the -g flag. So how do we get started by compiling? So we have to give the compiler information that it needs to put in debugging symbols into the executable. For that, you need to put the -g flag. So when you put the -g flag, the compiler introduces debugging symbols into the executable, but then you have to start the program within the GNU debugger. So the GNU debugger environment starts up, and then you put in the executable inside it, and then you do the execution of the program within the GDB environment. Obviously, this is going to slow things down, but our job here is to figure out what is going on in that program. So we can start GDB by doing GDB my program. If your program requires arguments, you can pass arguments to it as well. If the program is already running on the machine with certain process ID, you can then attach your GDB debugger to the running process as well, as long as it has the debugging symbols. So what are the key steps on using GDB correctly? You need to set breakpoints. Breakpoints are where logically the code will come, execution will come and pause, and once it's paused over there, you can then go ahead and inspect the different variables. Now you can set breakpoints in different locations. You can set the breakpoint at the main function. You can set the breakpoint at a particular function where the function is being called, or very explicitly you can say at a particular line number of a particular file, that's where I want to go and pause my program. Think about this as hitting a pause button in while watching a movie, and then suddenly you do some sort of investigation in the frozen scene. So you can then do this sort of thing. And then you can go and step over the next code by pressing different variables like n. So now let us see how we can use this in a simple code. So now I have a very simple code called hello, right? And this code is very simple. It's just going to take the string hello GDB and print out this string. Now I want to go and stop at this particular line, which is line number 5. So let's see how do I go about doing this. So first I have to compile the code with the symbols flag -g, and in this case an a.out is created. So to now execute this program, I have to now call the GDB executable and then run the a.out. At this point, only the GDB environment has been initialized. The program has been loaded in memory, but it has not, begun execution as yet. This is the time I want to start introducing the breakpoints before the execution of the code, because once the code starts running, then I'll have to catch up with it. Right? So now I'm going to put in a breakpoint, and I'm saying B, and in this case, I'm going to put it on line 5. I'll say this is my source code file, and I'm going to say line number 5. So this is what the breakpoint has been introduced. So if I say info B, at this point, it's telling me that at hello.c, line number 5, I'm going to stop. Now I'm going to run the program. So when I say run, the program will start executing, and it's gone and stopped at that printf. It has not executed that line of code. At this point of time, I can now figure out what the different variables are. I can find out what string is by saying pstr, and it tells me that it is hello world, right? I can do a little bit of a deeper inspection. I can figure out what the memory locations is, and this tells me that the memory location of str is here. This is the memory address where it is. I can also figure out if I just want a few bytes of this particular string in a certain format. For example, if I want to see this in a hexadecimal format, so I can say X, say I want the first only 5 bytes, which is the first characters HELLO, and I say this is the code for the hexadecimal bytes, and I say str, and now it tells me, okay, H corresponds to this hexadecimal number, E corresponds to this hexadecimal number, L and L corresponds to these hexadecimal numbers, and O corresponds to these. So this is a very useful way of sort of looking and inspecting memory, and this is a very simple example that we have given. So now I can just finish with continue, and it will keep on, and the process will exit normally, and it's printed out the hello GDB. So now let us go out and let's go back to our Laplace serial code and see what happens over there. So you can see this is the Laplace serial code which we have already written for computing the temperature distribution on this flat plate. We have the compute function. I'm not going to tell you the details of the compute algorithm, etc., because we have discussed this. So we're going to have the compute function which is being called over here, and then we have the copy function which is also being called over here. So now I'm going to set breakpoints on a functional basis, right? So in that case, what I'm going to do is, again, I'm going to compile this code with the debug information, and this time I'm going to put it out into a executable called Laplace, and I can now go ahead and do GDB Laplace serial. Now it's my time to put the breakpoints, and now I'm going to put breakpoints on the functions. So I'm going to put one breakpoint on the function compute. That means the code will go and pause right before compute is getting executed, and another breakpoint at copy. So if I now say info B, I'll see that there are 2 breakpoints. One is at Laplace serial 99, line number 99, which is the compute. The other one is Laplace serial, line number 111, which is the copy function. So this is where it's going to go and stop. So now when I say run, it will go and stop at the compute function. here now I can inspect different variables. I can inspect the value of the index I can inspect the value of index j, right? And look, I and j are at 1002 and 1002. That's because from the previous setting of boundary conditions, they have come to that. Whereas in this case, they are yet to be initialized to 1. Then I can look at the value of the variable t, and I can give it any sort of specific location. Let's say I say 5, 5, and hopefully it should be 0. Yeah, so the interior is still calculation is still 0. So I can then now start stepping through this function. I can now say next, it goes into the next line, goes to the next line, does all this compute, then goes here, then goes here. So it's keeping on doing this. So it's done this now for the index j. Now you will see that j has been sort of incremented. So if I now say pj, you see j has been incremented to 2 because the next iteration has gone on. So I can now step through each line in code and see how the index is moving. I can now figure out what t is being computed. So on and so forth. So tij in this case, right, starting from the right corner is still going to be 0 because you're going to do a lot of iterations for it to get some value. So ti11 will still at this point be 0. I can now say continue, and this will keep on continuing till I go to the next iteration, and it goes till the breakpoint 2. So now the whole compute function has been computed. Now it has come and stopped at copy. And then I can again sort of go ahead, say next line, next line, next line, next line, so on and so forth. And then I can say continue, and then it will go and like now stop at the previous compute. So now the last iteration has been done. So let's try to look at, see what is the value for p, t, 1001, 1001. So you can see that there has been a compute which has been calculated. So this has now, it is no longer 0, it is some value. We can also figure out what it is for 1000 and 1000, which is the last diagonal element, and you can see that has been correctly computed to be 50, right? Because of the last average has to be 50 in that diagonal. So you can keep on continuing this. Then I can just say run, and you can restart the run if you want, or I can just say finish. So then it'll keep going to the next function, and then you can keep putting on this. So this way you can step through each and every line of the code, then figure out what the variables are and do logical edits. So now we will quit this program. So you can examine the memory, you can look at different values, you can display the variable names. You can also do something called as backtrace. Backtrace essentially tells you which function has called which function has called which function. So that will then, in case there are some memory errors, you will know the entire call history of those functions. You can do advanced stuff, like you can watch a particular variable and you can break when the value of that particular variable changes. Let's say that there's some critical variable whom you want to watch the moment that gets touched, or that the value of it changes, you want to stop at that point of time. You can use the watch function and put the variable and break when the value changes. You can say when a particular variable is read, can I stop at that point of time? That will use the rwatch command. If you want break on just access, whether it is read, write, whatever it is, that is awatch, which will give you break on access. And it's very, very useful to analyze core dumps. So when you put the entire dump of the file about the entire history of how things are working, and if a program crashes, you can then figure out what is going on by just looking at the core dump. You can customize the commands by using the .gdb init file for custom commands, but that's basically for advanced users. Thank you.